Hey there, physical science students. This is Ms. Ruark. We're continuing with Unit 2 on motion and forces, and we're going to be talking about acceleration in today's podcast. All right, so acceleration and motion. We already have talked about velocity, and we know that velocity and speed are pretty much the same thing. The difference is that velocity is speed with direction. Okay, speed is distance over time. Velocity is distance over time with a direction in mind. Okay, well, we also talked about acceleration and said the acceleration is the rate at which velocity changes over time. We also said that acceleration is just a change in motion. Okay, so you should remember that from last chapter. We said that velocity is a change in motion. And I'm writing with my mouse, so if it's really messy, I apologize. All right, so acceleration, we've already discovered, can be made from a change in speed, so it can speed up or slow down, or from a change in direction. It can turn right, left, backwards, flip upside down, all of that. These are all things that can cause an acceleration. Okay, so centripetal acceleration. A centripetal acceleration is when a object is moving at constant speed and it's going around in a circle. And the constant speed's not going to change because it's constant. Okay, so moving around in a circle, an example of that would be this roller coaster going around in circles, or these kids on this merry-go-round going around in circles, and it's moving in a circle. So if the speed doesn't change, you would say, well, it's not accelerating. Wrong. It's accelerating because the direction that it's moving is constantly changing. If this roller coaster came off of this circle, oh, I need a different color. Let's change the color. Let's go yellow. All right, so if this roller coaster was going and it didn't change its direction, it would just keep going this way off the page, right? Okay, so it keeps coming this way. What if it stopped accelerating and it just went the same speed, but it didn't change its direction? Well, it wouldn't be accelerating anymore, but it also wouldn't be going around in a circle, and those people would be dead. Okay, so constant speed, but changing direction does mean acceleration. Okay. All right, so how do we calculate acceleration? Well, average acceleration, or acceleration for something in a straight line, is going to be the final velocity minus the initial velocity, and we're going to divide that by the time that it took to do that change. Okay, so acceleration, A, is equal to delta V. Okay, that's a Greek letter delta. It looks like a triangle, and it stands for time, or not time, sorry, change, the change in velocity over time. Okay, the units for acceleration are going to be meters per seconds squared. That squared there is very important. The squared there tells us that it is acceleration. If it was just meters per second, it would be velocity. Okay, so the difference between the two is velocity is meters per second, acceleration is meters per second squared. So pay attention to your units. A lot of times the units will give away what you're trying to do or what you're trying to solve for. All right, so acceleration, a couple things about acceleration. If the acceleration is small, it's a gradual increase in the velocity, which means that it's going to slowly speed up or slowly slow down or slowly turn. Right? If the acceleration is large, there's a rapid increase in velocity. So they're going to very quickly speed up or very quickly slow down, slam on the brakes, or hit the gas. Okay? And if there's a negative acceleration, it's because the velocity is decreasing, which means it's slowing down. Okay, so your positive acceleration is going forward, and your negative acceleration would be thought of as going backwards or slowing down. All right, so here's an example. We have a flower pot here and it falls off a second-story windowsill. The flower pot starts from rest and then it hits the sidewalk 1.5 seconds later with a velocity of 14.7 meters per second. And they want us to find the average acceleration of the flower pot. All right, well, we know that we need, for acceleration, we need to find the change in velocity over time, which means we need to have a final velocity, we need to have an initial velocity, and we need to have a time. All right, so what you need to do is go through and circle everything in this word problem that is important information. Okay, so a flower pot falls off a second-story windowsill. Well, that's important, but it's not important to our calculations, so we're going to keep going. The flower pot starts from rest. Well, if it starts from rest, that means is it moving or is it sitting still? And if it's sitting still, how fast is it going? Trick question, right? If it's at rest, that's important. We need to circle that. That means that its initial velocity is 0. So it's starting with no velocity. All right, it's going to hit that sidewalk 1.5 seconds later. That's a time right there. We need that. And it has a final velocity of 14.7 meters per second. So final velocity, remember when it's done moving, this is its final velocity. When it starts, this is its initial. And they want the average acceleration of the flower pot. All right, so here's our equation. We need to plug these values in. So initial velocity is 0, final velocity is 14.7, and the time would be 1.5. So we plug those in. 14.7 meters per second minus 0 meters per second over 1.5 seconds. Okay, when we plug this into the calculator, make sure that you do the numerator first and then divide by the denominator, and you should get 9.8 meters per second squared. Okay, not so bad. I don't think it is anyways. It's just a matter of being able to understand what you need from the word problem, and we'll practice that. Okay, example number 2. So a car accelerates from 0 meters per second to 45 meters per second northward in 15 seconds. What's the acceleration of the car? Okay, so they're telling you the direction that the car is moving. So it says it accelerates from 0 meters per second. That must be its initial velocity. And it accelerates to 45 meters per second, which must be your final velocity. And here's your time. So you have this and your time. And they want to know what is the acceleration. Now, a lot of people forget what are we looking for. So underline it or box it in, one of the two. I didn't mean to draw that line there. Okay, so we're going to plug this into our equation here. A is equal to the delta V, or the change in velocity over time. So 45 meters per second minus 0 meters per second, and divide that by 15. And plug that into the calculator, and you should get, and you should be checking your calculations with me so you know how to do this. You should get 3 meters per second squared northward. Now remember, this is an acceleration. It is a vector, so you have to have a direction. All right, well, part B of this. After reaching 45 meters per second, the car slows down to 0 meters per second in 10 seconds. And they want to know what is the acceleration of the car. All right, so I want you guys to try this on your own and then pause it and come back and see how you did. All right, so welcome back. Here we have 45 meters per second. This is where it starts, so this would be our initial velocity. Here we have our 0 meters per second, which is where it ends up, so that's our final velocity. And here, 10 seconds, we have our time. So we're going to plug that into our equation. Okay, final minus initial, so 0 minus 45 over the time, which is 10. And when we solve this, we should have a negative 4.5 meters per second squared northward. Okay, and so this is going to be a negative 4.5, which means that it's slowing down, and it's slowing down the opposite direction, which means it's accelerating in the opposite direction, okay, because it's slowing down. All right, graphing accelerated motion. So speed can be determined from a graph of distance versus time. We saw that in class the other day. We had a graph, we had time, we had distance. Now we didn't calculate the average, I should say distance. We didn't calculate the average, but if we had a graph like this, in order to find the slope, m, it would be rise over run. Right? Well, rise over run in this case is going to be distance for rise over time, and that gives you velocity. So you can actually find the speed from the graph of distance versus time. You can also graph acceleration and find that from a graph of speed versus time. Okay, so if you had that, you would have your graph, and you would have speed on the vertical, and you would have time on your horizontal axis or your x-axis. Remember, time always goes on the x-axis. Okay, and to find that, it would be the change in speed over time. So here your slope would be the change in speed over time, which ends up being acceleration. How nice is that? All right, so a straight line slope or a straight slope will give a constant acceleration, and if the slope isn't straight, then that means that the acceleration is changing. If the slope is going up, meaning you have a positive slope, it's positive acceleration, so you're speeding up. And if the slope is going down, it's a negative slope, and that means that it's slowing down. All right, so here's another example. We have a bus traveling on a straight road at 20 meters per second uniformly. What does that mean? Well, that means that it's consistent. It's the same. So it uniformly slows down to a stop over 20 seconds, which means it's slowing down at the same rate. Okay? The bus remains stopped for 20 seconds, and then it accelerates at a rate of 1.5 meters per second squared for 10 seconds, and then continues at a constant speed. And they want us to graph the speed versus time for 60 seconds and figure out what the bus's final speed is. All right, so remember, time is always going to go on the x-axis. So time will go on the bottom, and your speed will go on the y-axis. Okay, and they want to know, they want us to graph all this. So it's a bus is traveling on a straight road at 20 meters per second. So that's its speed. And it's going to slow down, and then it's going to speed up. Okay, so we've got to set up our axes here, and I'll go on ahead and set this up. I'm going to do it by 2. So this would be 2, 4, 6, 8, 10, 12, 14. I'm just not writing them all in. 16, 18, and then of course 20. I'll write that one in because it's there. All right, and then for my time, I think I'm going to go by 5s. And it doesn't matter if your scales are different as long as they're consistent. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, not done yet, huh? And 60. All right. So a bus traveling on a straight road at 20 meters per second. So here we are, 20 meters per second. Okay, and it slows to a stop over 20 seconds. Okay, so it's going to go from 20 all the way down to 0 meters per second in 20 seconds. So I'm going to have to start there, and I'm going to finish here. And it's uniform, which means it's kind of going at the same rate. So we're going to hope that I can draw this in a straight line. All right, so down here like this. Okay, the bus remains stopped for 20 seconds. So it's going to stay here like this for 20 seconds, which means it probably came to a stoplight or stop sign. Okay, and then it accelerates at a rate of 1.5 meters per second squared for 10 seconds. So for 10 seconds here, it's going to go up 1.5 meters for every second squared. So we're going to go up 1.5 meters, so we're going to go up 1.5 for every 10 seconds, which means we're going to go up to probably about a rate of 15. So by the time we get to 50, we're going to have to be up here at 15. Okay, and we come back up, up like this. Okay. So what's the bus's final speed? Well, the bus's final speed should be 15 meters per second. And how did I figure that out? Well, I said, look, guys, we have 15 and 10. And remember, acceleration is equal to the change in velocity over time. Well, I took the time and plugged it in here. I'll never do that. Okay, took the time and plugged it in for t. We're looking for v, and we know the acceleration is 1.5. Okay, to solve for v and get it by itself, we've got to get this over here. So to get the 10 to the other side, we multiply both sides by 10. And if 10 times 1.5 will give you the velocity is equal to 15 meters per second. All right. And here's a little physics humor for you, and I'll see you in class.